Okay. So those who are not here, we just went over the questions. First was Abhinav Sairam about the value of A, which we say cannot be more than pi by 2 because the probability becomes more. The second question we just discussed was that you cannot compute expectation from the cumulative. Hey, you guys don't come to class often, is it? Acha, you sit at the back. You also sit at the back? Because I see this 6-8 girls sitting here, I don't see at the back. Alright, so the second question we were doing was that you cannot compute the expectation from the cumulative distribution function, but there is a relation between the cumulative distribution function and the probability density function. Integral of the PDF is CDF, differentiation of CDF is the PDF. So get the PDF out if the CDF is given to you, multiply it with the variable, integrate it in case of continuous or sum it up in the case of discrete, and that is how you will compute your expected value or expectation. So those are the two things we did. Now I again forgot your name, I'm sorry. Aman. So we come to Aman's question. Although this may have already been answered, but this was today what he asked. So let's say X has following PMFs. I am writing a PMF, so it implies that it is a discrete random variable, and it is given as P of -1 is 0.2, any numbers I can take, P of 0 is 0.3, P of 1 is 1, and you have to compute the expectation of x square. So you are asking now whether square root, what will happen. So there is a direct mapping, you don't have to worry about it, because what y is equal to some square will map something, x is equal to the square root of that, direct mapping would be there. Like, sorry, I'm talking and writing. Any number less than 1. Okay. So I said y is equal to x square. So expectation of x square and expectation of y. Do this box bracket, please. No? If I do it wrong, you will do it wrong. Sure. So this will be, the numbers will be squared, so it will be -1 square. Probability of y is equal to -1 square plus 0 square. Probability of y is equal to 0 square plus 1 square. Probability of y is equal to 1 square. So this will map to x is equal to -1, this maps to x is equal to 0, this maps to x is equal to 1, so you don't have to think. Is that okay, Aman? So even if there is a -1, you're not technically making a square root anywhere. You are just doing a mapping back to x, and there is a direct mapping there already. Everybody okay? Alright. So we'll start with variance.
Upon differentiating the CDF, how do we get upon
So actually I have not worked it out, it was directly stated in the book that it should be equal.
Fundamental theorem.
Which theorem?
Second fundamental theorem.
So what does it say? I've forgotten all integration
F
differentiation.
of A minus.
You got it?
What is the antiderivative?
We can take
Fundamental theorem antiderivative.
You can take the differentiation inside, is it?
You can eliminate
So what will happen to infinity then? I'll have to think it over. I've not done integration differentiation for a long time, but I can tell you on Friday. Let me just look it up for those who did get it. But ideally, the answer will come at f of a. How it comes, we'll see later. Sorry.
We take a as a variable and the formula for differentiation of integral is a dash f of a minus negative infinity dash into f of negative infinity. So negative infinity's differentiation will be 0.
Okay.
And a's differential with respect to a will be 1. So it comes out as f of a.
Okay, you do it for them. No, I'll write in the meantime. Come. I don't remember. No, it's better you write it down. What's your name?
Manan.
So Manan will write. Till the time I'll write the variance thing. He'll work it out.
F of minus infinity को भी इसमें derivative जो डी करोगे ना उसके बाद
dy dA of f of x उसका डेरिवेटिव लेकर f of x minus f of
F of minus infinity का डेरिवेटिव
Okay. So in the lecture today in the morning we talked about expectation of a random variable. What is expectation of a random? Let him finish, then we'll talk. है ना? We'll see if he's done it correctly. So what is an expectation of a random variable? Jago. हाँ. It's just the variable multiplied with its probability and everything added up. That's the introduction. That's how it's defined. For a discrete random variable, it's just the product of the variable with the probability mass function. And you saw the case of rolling a die and you just do 1 times 1 over 6 and so on and so forth. Then we saw expectation of x square, which you can see the functional composition of function just goes inside the x variable, not inside the PMF. That is what we told. Then we did it for the continuous random variable. For the continuous random variable, the x. Okay, you've done it? Okay.
Actually, the differentiation is the differentiation of this function.
Acha, it's the limit function and
b of x a of x function of x with
Yeah, these are functions. They can be constants also. Then it
हाँ
will be
ठीक
0.
है they function of x ठीक है चलो ठीक है b prime
So we take this a as a variable because we calculate the PDF and we differentiate this respect to a. So it comes a dash comes out as 1 and then it remains as a.
but infinity is, why have you made it 0?
So negative infinity will be any constant. It's not a function.
of it, so it's a constant.
So its differentiation will be 0.
Acha, it's a constant, right? Correct.
Not dependent on
ठीक है good. Thank you. Is it okay? Manan has done it correctly. The derivative of the constant is 0, that's why it vanishes and you get only the first term and that remains as f. ठीक है? Alright. So where were we? So we were talking about the continuous random variable. For the continuous random variable, the x multiplies with the probability density function inside the integral, and then we did one example. Then we did 3 properties of expectation. One was when you're doing composition of function, which you saw in e of x square, the composition goes only with the, in place of the x, not inside p of x in discrete. In case of continuous, it goes in place of x, not with f of x, the PDF in case of that. Then if a x plus b, it's just a of expectation x plus b, and then if you're adding a random numbers expectation, then it is just individual sum of the expectations. That is what we did in the first lecture. Okay. So now we're going to talk about variance. To do variance, you know variance, actually you've used statistics, but we are talking in terms of random variables. Let's say there are w, y, z, 3 random variables which are given as 0 as follows. W is equal to 0 with probability 1, y is equal to minus 1 comma 1, both with probability half, and then there is a z which is minus 100 to 100, again with the probability half in both of them. So if you look at these 3, is that clear or should I write it bigger? Oh, everybody okay? So if these are 3 random variables, what's the expectation of these? 0. Everybody agrees? Done it in your head? It's just the multiplication of these, no? This into this, minus half plus half minus 50 plus 50. So the expectation of all of them is 50. So expectation is not a good measure of telling everything about your data. That's what it says. So we'll look at how the data is varying around the mean value. So that is why we look at expectation as the variance. So the variance could be actually defined as x is equal to an expectation of, let's say, x minus mu, if mu is the mean values or the average value or the expected value. So what is the problem with this definition of variance? We don't use this. We use the squared value. Rather we use expectation of x minus mu squared. This is how we define the variance, but why do we define it this way? What is the problem with the first one? Sorry? Well, yeah, it's the differentiability is also a problem here. If you look at the absolute function, it is not differentiable everywhere, right? So that is why we work with something more easier and they square it in this. So now we go to simplify it. So variance of x is, so we'll write it as e of x square minus 2 mu x plus mu square. What will we do? Can we pull it inside? This is a random variable. Is this a random variable? Because there's x. Is this a random variable? No, it's a constant. It's the mean value. So this will be expectation of x square minus 2 mu expectation of x plus mu square. So what we are saying is mu is nothing but expectation of x. The mean value is we are referring to as the expectation value, expectation of x. So this thing is equal to x square minus so that's the definition of variance. Okay, some properties. That was the intro. For constants a comma b, all these you can prove, like we wrote 3 for this, we'll write 4 for these. Variance of ax is equal to a square variance of x. This is obvious because the square is there inside this, so it will get pulled out as a constant. The second is variance of x plus b is equal to variance of x. B doesn't play any role. Now of course you can write this together, it's the same thing. The fourth one is important, that variance of x plus x, let's say we are doing this, is not equal to variance of x plus variance of x. Or variance of x plus y is not in general true equal to variance of x plus variance. You can prove this. So you have to remember it, it behaves differently than the expectation, where you can add it the random variables, the expectation of the random variables. Everybody okay? So we'll do another problem. We'll do two problems actually. We'll do one problem with the discrete random variable, one with the contiguous random variable. So it says compute the variance of x if x represents outcome of rolling fair die. Can you do it? I'll write the next problem in the meantime. Given PDF of a continuous RV x as f of x equal to x 2 minus x 0 0 is less than x is less than 1 is less than x is less than equal to 2, otherwise find the variance of x. Have you done it? 35 by 12, correct. Is all of you done it or just Manan and Tanvi? Okay, that's fine. So that I you understanding it. So okay, I think most of you have done it already. This is the same problem which we had done in the case of expectation. So the expectation of x we had computed as 7 by 2 already. What did we need to compute? Expectation of x square. So this would be 1 square into 1 over 6, 2 square into 1 over 6, all the way till 6 square 1 over 6. So you can think of it as, sorry, everybody okay, or should I write more steps? You've done it so many times, right? Either you can apply the proposition that f of g of x you applying the square function, or you can write it more explicitly as y is equal to x square and do it. Everybody okay at the back? So which means that the variance is, so this turns out to be 91 over 6, 7 over 2 minus 91 over 6. Sorry. Should not do it too much in a hurry. 91 6 minus 7 over 2 square. Okay. To do this one, it's also straightforward, but it's a good idea to do it once. Expectation of x is integral 0 to 1 x into x dx plus integral of 1 to 2 x into 2 minus x dx. Once you do that, you will get 1. When I do expectation of x square, then again by the proposition what happens? X square, this will only change. The PDF will remain the same, plus 1 to 2 x square, this changes, this remains the same dx. Once you do the integration of this is 7 over 6. So I came to know that in the quiz many people have not attempted part of third problem and fourth problem. Was it the quiz too hard for you? Huh? Sorry? Fourth was a little confusing. I had to make it slightly harder. No, it's, just to have a little, so that everybody doesn't get 20. But anyways, you can. I don't deduct marks for calculation mistakes. That's not the focus. So I just want to see whether you got the concept or not. So if in the exam you write this correctly, then you get most of the marks. If the integration fails, then don't worry about it. But doesn't mean that you don't do it. So you do it. If you do a mistake, then it's okay. So this is 7 over 6. So the variance is okay. So straightforward, variance is not too bad. These identities are sometimes difficult to prove, otherwise these are straightforward concept. The last thing which we look at today is covariance. Do you have a class at 3:30? So if we take slightly, although I think I'll finish, but that's okay. So what covariance means is that you're trying to look like the jointly distributed random variables. Now we are going in that direction, that there is an x and there is an y, and how are the two related to each other? How is the variation in one related to the variation in the other, or the other one related to the first one? So the covariance of two random variables x and y is written as this is intuitive because you will see it comes back to the variance when it is of one variable. I have slides also on this which I'll show you how are the two sets of variables related more figuratively. So if it is only variance of x, then it's x minus mu x square, or it is y, it's that. So now has one set of variables varying with respect to others. Here you are finding this. So again we'll simplify this formula. So to simplify this formula, we'll write it as e of, this will be xy mu xy minus mu y x minus mu x mu y. Again, it's an expectation, so we'll take the expectation inside by the this is plus. So we just expand it. So this is x of xy minus mu x ey minus mu y ex plus mu x mu y. Now mu x is expectation of x, mu y is expectation of y. So all of that will cancel and you will be left with xy minus e of x e of y. So some properties of covariance, like You've seen it for variance. The first property is that the order doesn't matter. I think it's called it associativity, we call it, or what? Why commutative? Sorry?
Commutative.
Commutative, yeah, they're commutative. Covariance of x comma x is variance of x, which you have already seen. Third is covariance of ax comma y is a of covariance of x comma y. So a comes out, and then covariance of x1 plus x2 in presence of y is equal to covariance of x1 plus comma y plus covariance of x2 comma y. So for proving some of these, I think you would need that jointly distributed random variables which you have seen. The distribution of a, what is the distribution of a joint random variable, or what is the joint probability mass function, or what is the joint density function. So all that is needed in proving this, but we are not doing that. Now the question is, if x and y are independent, they're independent, then the covariance of x comma y is equal to 0. So that's it. I'm not giving any problems on covariance. There will be no question in the exam also because we are short of time. But in the slides I'll show you more examples of covariance, real life, more pictorially, which because it arises in real life. Covariance is very important because you have two sets of data which you have to sometimes play around with. So what you can do is take a few minutes break if you want. I'll turn the projector on and then I'll go over the slides. So this is what will come in the exam. I've also uploaded a PDF in the supporting material section. I'll show you about the Bernoulli distribution, which is a discrete distribution coming from a discrete random variable, and a Gaussian or a normal distribution which is coming from a continuous random variable. So you can read it so that you know what you should be aware that these exist. That's the idea. But the exam will be only until variance. So that is what we'll do. So I'll open this, show you that PDF, show you covariance, and then give you an idea of machine learning. So where all this is coming into play. You can take a break if you want. Here you can turn the projector on. Let me erase it, otherwise somebody who comes here will complain.
Yes.
Recording is still going now?
Recording.
Don't stop it. Let the whole thing get recorded.
Yes. It is on the camera, it should be your screen.
It should show the screen.
So just check with the brain within here.
Call him.
It's about 320.
Multiple dx में divided. It is a small rectangle. So once the x plus dx के gain पे f of x का value constant. So we are just multiplying the values of x by the point. The point is itself dx.
Defining
What is the expectation of?
Single point of probability.
E of?
Over the entire block.
be defined. Affects the point. It's a joint distributed. If they are assumed to be independent of each other, then it's the product. But if they are not, then I need to check. I don't know. इसी का रिकॉर्डिंग चालू है चालू है चालू है ना बस स्टॉप करूँगा तो परफेक्टली ठीक थैंक यू
So, way covariance is used, I'll briefly show you. These formulas are written in a different context, so I don't want to confuse you. Don't look at the formulas before this, which I showed. But there is a Pearson correlation coefficient which takes the covariance between two sets of data points and then divides by the square root of each of the variances. So what it measures is the strength of the linear relationship between two variables. So don't read this, it's better is look at this. So if there is x and y, if you there's the x set of data points, there's a y set of data points, and they turn out to be this way. The Pearson correlation coefficient, which uses the covariances and the variances, turns out to be this. It means that they are negatively correlated. They are strongly negatively correlated. Here they are weakly negatively correlated. Here there is no correlation. When the line goes positively up, you say that they are positively correlated, and then this one strongly positively correlated, weakly correlated, and this one is not correlated. They can be a curvilinear relationship also.
R equal to 0, y at 2 plot.
Sorry?
For R equal to 0, y at 2 plot.
Well, it's
Like, shouldn't it mean the same one thing?
it's telling the same thing, that there is no relationship between the two, except that these are sparsely distributed, these are more tightly towards the line. That's what it's trying to tell. But they can be curvilinear correlation as well. It need not be just linear. You can see there's strong relation, there's weak relation, there's no relation. So don't go to the formulas, because we're using slightly different set of formulas. Here we are telling how to compute it. Anyways, so that's a little bit about covariance and correlation. What I was telling you is uploaded here, is uploaded here under the distribution, under the supporting material tab. So you can just read it and know what, at least you should know what two distributions are. That's why I have not done too much on it. I'll not ask this in the exam, but at least read it. What is a Bernoulli? You should know. Bernoulli is that it can only take 0 and 1, the random variable, and the probabilities are also p or 1 minus p. What is a normal distribution? Now you know what is a Gaussian. It is dependent on the mean and the standard deviation. It takes this as a PDF, and there is no closed formula for a CDF for this. So you can just read it for your leisure, so that you know you are aware of this. Okay, now what we'll do is we'll start a little bit on machine learning. So you can close all your notes, because don't write anything. It's nothing for you to write. It is just to show you, because the goal, I'll just run through slides, because the slides I'm going to go through is, it will take 5-6 lectures if I start explaining everything. What I'll just show is the places where gradient is used, Jacobian is used, optimization is used, probability is used. That is what I'm going to just show you. Just an overview. So before I do that, we'll first see what is machine learning. This slide is for that. So there are three parts to this. What is ML? The heart of ML is models, which you'll see in a minute. And then there are types of learnings in model. So what it's written is that you want computers to, do work for you, whether you want to navigate on Mars or you want to change solution for a particular case. All that can be done automatically by computers, and that is machine learning. You can think of it that way, that for example, you are trying to predict, you're given a set of clouds are approaching Simrol, and it's very dark set of clouds, and you know how much humidity they carry, and there's some information too, and you want to predict whether the rain will come or not. So one way of doing, which the scientists have been doing for so long, is to take PDEs, partial differential equations, and model them, in the sense that no, this is a water-based model, so Navier-Stokes equation will play a role, or there is stress involved in the crowd, so there would be some sort of stress equation involved. So you can build a bunch of equations and then at the end of it predict. What machine learning is doing, it's not creating any of these mathematical models, creating a black box, that you're giving humidity, rain, whatever, humidity, sunlight, viscosity of the cloud or whatever is there, and then it's just predicting. So there is a black box, but internally it's building a function. So the challenge in machine learning these days is we're going towards explainability or interpretability. We don't want it to be black box. We want it to interpret what's going inside it, what the neural network is doing. So that's machine learning. So machine learning is concerned of using the right features to build the right model to achieve the right task. What it means is, the task is, for example, in this case, predicting the rain. Model, which we're going to spend some time, the black boxes, how you'll build the models, and features are the properties of your data. So your data, if the data is a cloud, the properties about that cloud would be there. How large is the nimbus cloud, it is that cloud, whatever, blah blah blah. So those are the features. we call features as the workhorse of machine learning, because your model will not work well at all if the features are not selected or curated properly. So the data has to be accessed well. So this is one of the big figures where you're acquiring the data, you're doing the feature part where you can see transformation, normalization, cleaning, encoding, pre-processing, blah, blah, blah. And this is where you are doing your model part, where we'll do most of the work and then you are deploying it. This example I think is a good, it's trying to, I think spam and ham is this one. Okay, no. So for example, you're taking the feature, this is the model, this is the learning algorithm which is updating your model by getting trained with the data. Once it's trained, then it starts predicting with that data. So that's what's the only thing showing. So this is the second part of machine learning where most of the work happens. There are three kinds of models which are categorized. One is a geometric model. We use hyperplanes, transformation, distance metrics. They are probabilistic models, which you'll see now. They are also logical models. When we say logical models, it's something like a decision tree. The trees which you're taking data structures, no? So you build trees of data and then you try to predict something. Once you have the models, you have to check how good your models are. So you can, check their accuracy, precision, recall. These terms are just telling you how to check your result is correct or not, because often you don't know what your result should be. So these are some measures which people have created. Okay, then you internally build a function and you do some sort of a optimization which you will see today. So there are different optimizations which you do: combinatorial, convex, constraint. And then how do you train your model? You do supervised learning or you do unsupervised. Ignores reinforcement learning. I don't want to explain you that. What supervised learning means is, for example, you're classifying a set of emails as spam or ham. So you already know the labels. So that part is called supervised learning because you know the labels beforehand. But given a set of data, like I say this whole class is there, I want to put you into some clusters based on, some feature. I say just cluster them. So there'll be some metric which will use. I would not know what are the final good cluster. How many 10 of you go here, 5 of you go there. There is no fixed answer. So this unlabeled data, when you look at it, it's called unsupervised learning. Yeah, I think that's what it's showing. Given x1, y1, learn a function to predict each dimension corresponding. An example which I give is, given a set of mammograms or cancer or x-ray images or some sort of images which tells you whether this is a cancer or not a cancer. So you would first train your model saying that this is a cancer, not a cancer, and then the new data will come and it will tell that this image is cancerous, this one is not. So that is supervised learning. Unsupervised, again I give an example of plant data. Given a set of genomes of plant, whole genomes, I have given an example before. Every plant, every living being has a sequence of characters associated with it. Now you want to group them in different categories. You would not know what categories are at the end, because there could be a category of plants, say disease resistant, drought resistant, rain resistant, but all this has to be done by the algorithm itself. So it's an unsupervised technique. Yeah, okay, so these are some data set repositories. These are some places where you go for conferences. Okay, so that's a general overview about machine learning. What I want to show you is places where vector calculus is used, optimization is used, and probability is used. So those are the three insights I'm going to give. So first one is we look at regression. So we'll skip correlation. We'll go to regression. What is regression? What does the word regression mean? English word. You don't know? Nobody is preparing for GRE or TOEFL. You don't know what regression is. Regression is saying that you predict something with data. That's what regression is meaning. Ayush, can you get water from the floor below? This floor doesn't have. So what it's saying is, let's say you're given this set of data points in space. We want to say what is the curve which best matches them. That is what is called regression. So one way could be you just draw a line and see which is the line which closest resembles these. You know, this is a line, this is a line, this is a line which captures all the data point. Of course, ideally it would be a curve. Maybe that is of degree 100 or 10, or I don't know what degree it would be, but let's say we are doing linear regression. So this would be the line which you would want to put. Then to compute the equation of the line, we'll project onto this line from every point, sum the errors and try to minimize it. That's what our goal is. So we'll take the predicted minus actual. So this is the equation of the line. There is an error associated with it. Let's go to the final equation. So let's say you are predicting a line, and these are the variables which you don't know, and this is the dimension of the data. It's a d-dimensional data. So don't try to understand this. We'll go. What I want to show is that you will apply a gradient descent approach. You learned gradient descent with us. There is a gradient involved, and you actually there is an example also for this. You can see you start in the space somewhere here with prediction. You're trying to predict the line. Remember, you started with this red point on this contours. Contours are the place where the function has same value, and then it moves, applies gradient descent, and finally reaches a minima. So that is where, and this will give you the final thetas which will define your regression line. Everybody okay? So this is a geometric model. It's a model which is, now that you given 10 points, you predicted the equation of the line. Now you will get another data point, you will tell what's the y value. So that's the simplest of the models. More difficult models are the SVM models, which I'll explain you next. So what SVM models does it's called a support vector machine. The name support vector machines will be clear after I finish this discussion. But this is not predicting any function of the data. Like in regression, we were telling what line is represented by this data. In a support vector machine, the task is to classify the data into different classes. Given a data, find a line which separates the data, and then when the new data point comes, tell which side it belongs. For example, I am given a set of cancerous images, non-cancer image. I'll put them in space, draw a hyperplane between them, and train my hyperplane. This is the best hyperplane separating the cancer from the non-cancer. Now a new image comes. Does it fall on the cancerous side or on the non-cancerous side? So my goal is to tell what is this hyperplane, the geometric model which best defines. So the figures which you just saw in a minute, these are dark ones. Let's say these are cancerous, these are non-cancerous. This is equation of a line. But this equation can be formed in many ways. I can form it this way, I can form it this way, I can form it this way. So there are multiple ways of building the model. Which is your best model? So that is what we do in support vector machine, which you'll see in a minute. What you do is you take an arbitrary line, create some margins around it, and try to maximize these margins. Because the further this line is away from the data means it will be the best fit. So you create a math model out of it. You, in a n-dimensional space, you say this is the equation of my line. This is n-dimensional, this is n-dimensional too. This is a hyperplane, and then you create some +1, -1 margins about it. Once you get this margin value, you say I am going to maximize this margin. And margin can be written in terms of the normal to the plane, which is W here. All that math we'll do when you come to this, but what I want to show is eventually it becomes this. Eventually it becomes an optimization problem. Finding this hyperplane in a support vector machine is minimizing this subject to a constraint. So there is a lot of work involved in it. You saw optimization with me. So you will do optimization class where this will be more clearer. So there's a lot of math to this. There were few doubts. Okay. Okay, this is this much only. Then we do an example. We do, okay, this is important. So once you have the optimization problem, which is this guy, how do we solve it? We build something called as a Lagrange function. Did I teach you Lagrange function? Yeah, so you're just taking the objective function and taking the constraints inside it and building the Lagrange function, and then applying something called as a necessary and sufficient conditions, which I don't know whether I've told you. Did I tell you those? Okay. So those we apply and then we solve them and blah blah blah. So now of course all this is being done by the computer because they are solvers for this. But in the optimization course which you'll study, I'll tell you these necessary sufficient conditions. I'll tell you how to solve it. I will develop algorithms around it. So all the heart of SVM will be optimization. That's what I'm trying to tell you. And SVM is the biggest competitor to neural networks these days. So it is for classification tasks which you typically do. We're just solving them, I think. Yeah. Okay, so that we saw a little bit of vector, we saw a little bit of optimization. Now I'll give you a flavor of probability where this is used. Okay, so this we did in the very first, when we did Bayes theorem, we talked about this, if you remember. What is PY? PY is the data of prior probability where you've not seen the data, the probability of the class, and PX is the data of the probability of the data. Then we said what is likelihood probability. Let's say you have a problem where you given an email, you want to classify it as spam or not a spam or ham, the example I give. Then you look for words inside the image, lottery, Viagra, and so on and so forth. So this is called the likelihood probability, and the probability of the class looking at the email is called the posterior probability. That you have looked at the email, you have seen the words, now tell whether it's a spam or not a spam. So your model which we build around is something called as the maximum a posteriori rule, that you want to tell which class it belongs to or which maximizes this probability. You use the Bayes theorem, you convert it into likelihood probability. I know I'm going too fast, but the reason is not to explain you everything, just to you just see a glance of, get a glance of what is going on. Okay, so the naive Bayes classifier, or let's do the example, I think that would be best. So that you can see a real life example. So this is an example of the classifier which I have built by a probabilistic technique. I'll tell you what the probabilistic technique is. Let's look at an example. So you have given a data set, you have given certain words, lottery, Viagra, dollar, and it's telling you that when this is a training data which is building your model, which is telling that in this case the email will be definitely categorized as spam or not a spam, yes or no. So if it doesn't contain lottery but contains Viagra, it's definitely spam. If it contains lottery, Viagra, it is not a spam, which is surprising. But if it contains all the three words, then also it is not a spam. Whatever, the data looks rigged, but nevertheless, let's say this data is given to you and now your goal is to predict if it comes out at 0, 1, 1. If you see this data, how many possibilities of data is there? Only 8 combinations, right? Because there are 3 properties and each can take 0 and 1. So it's 2 into 2 into 2, 8. Although I have given data for 6, which means there are these 2 sets of data which you need to predict by building your model, correct? So what we'll do is, we'll build a model. For that, we'll first compute the data probabilities, which is given by this. The data probabilities is just looking at the final class, yes or no. We get data probability. Then we build likelihood probabilities, which is P of X oblique Y. And then by using the Bayes theorem and an independence rules, which I have not told you that every feature independently affects the decision, we build the classifier. So what it happens is, this is the classifier which I have not explained you. but it says that the probability of a yes for this new data point is 2/7 and probability of no is 1/27. So the probability of yes is higher, so hence it will be categorized as spam. That's okay. I've put a lot of details under the rug, independence and so on and so forth. So the probabilities are used quite in detail here. There is an example where using a Gaussian distribution also, but I think I'll just stop here. It was just to give you a flavor of where things are coming. Is that okay? Did it make it slightly better that you're not studying all this for some reason, not for, just for the sake of it? Okay. Alright, so we finished the classes. Everything is done from my end. On Friday, 5:30 you come, we'll show your quizzes. Like Ayush is grading quizzes, typically the TA's grade, midsams I'll grade, hai na? But you will get a chance to see. The solutions for the quiz are on the portal. You can take a look of them when you come at 5:30. If you have a doubt, then ask me, and I'm not too particular about marks, but you should have done something. I can't give 20 for doing nothing. So you have to do something, so you can check how harshly or leniently I grade. I think I grade leniently, but you can just figure that out. And we'll also upload 12 practice problems from probability. Please read it. Probability is not hard. Whatever I have done is very basic. The only thing in the trick in that is the terminologies that you should be aware of. That's the only idea I am telling you. And then good luck. Then after that your exam, and then Chandresh will come. He'll start with the first the part. Well, his topics are fairly straightforward. Linear algebra is there. It's not too complicated. Then some machine learning models he'll tell you in the class itself. That okay? Oh yeah, तुम लोगों ने कुछ greet ही नहीं किया वहाँ पे. Ministry people said, oh you guys are going, you will be treated as heroes in your institute. My father said, what hero? I mean there two people, I'll tell you, there were two people from Madhya Pradesh who got it in higher education. So there were 16 people across India in higher education who were given this award. And he is from Central Sanskrit University. He sent me the video. As soon as he reached the university premises, there were people with dhol and then with mala, and they were putting on him, and then students were touching their feet. मैंने कहा क्या बात है, मैंने कहा यहाँ तो कोई पूछ ही नहीं रहा, Anyways, so the interaction was really good. We initially one day was the whole rehearsal, first day Wednesday, because the president cannot, time is very precious. The president was very nice. She actually personally congratulated everyone. So when we were taking the award, the photos are on Instagram, Twitter and everywhere you can see. So she said congrats, and I was like, oh really, she's talking also. I thought she would just give the award and go. So she was nice. And then the next day the Prime Minister's house is so secured, you can't carry, you have to just wear your clothes, nothing else. You can't even carry a pen, that's what they say. So it was nice. He's a very down to earth guy. I mean, he's funny, he was humorous, and there were people who had selected to talk, those who would, like, there were school teachers also who were awarded separately, so they were more interested in school education than higher education. So because school education is more colorful, these teachers use puppets to teach the children, there's all sorts of innovations they do, they work really hard. So he asked about everyone. You can see the video is there, 2-hour video interaction is there, 1.5 hours, and he talks about that. Then he was very funny, but whenever somebody is saying, he would crack a joke and make everybody laugh. And finally he said, you take your students for tours. He's very focused on India's development, that you can tell, irrespective of whether you support Congress or BJP. But what I don't tell whom I support, and I'm not a pro BJP, neither I am a pro Congress. Doesn't mean that I am a Aam Aadmi Party. I'm not that either. So irrespective of your political inclinations, he is interested in, everybody has their negatives. If you look at the Gandhi family, or you look at, that's a different story, but he is focused on making India develop, the Viksit Bharat. So all his intentions are inclined towards that only. He said, how can you boost the economy, how you can do this. So he was suggesting school teachers that you take children for tours, take We have done a contest of what are the top 10 places in your state where everybody could go. The government will build the infrastructure, because once the infrastructure is there, people will start getting the economy go. He was saying we have missed the boat of domestic tourism in India. Once the domestic tourism is boosted, the economy will grow faster. So yeah, so in that sense he was suggesting, and he was saying every one of you are doing some innovative thing. We should highlight that. You should be mentors of other teachers and so on and so forth. So let's see how many people they asked me to mentor. Okay, so it was really good. It was a lifetime experience. Yeah. All right. So I'll see you on Friday. Thank you. You guys have congratulated me. I told my father they have congratulated me long ago. They have done it twice. The day I received the award, he had already done it. So we'll have some party. I'll try for a pizza. If it's not, then we'll do samosa or something. I don't know. I do want to do pizza, but it's up to Ayush to get it here to the campus. He will do it. Okay. Thank you. Ayush recording. Hey, I spoke what all you remove that, huh?
I'll crop it off.
Political affiliation.